So, hello everyone from my side and welcome to this presentation, which will be about time integration methods and I hope in particular about next generation time integration methods. So it's like within Star Trek where you hope that this is how the future will look like. There are plenty of them available and I could talk about all of them, but I'd like to specialize in one of them, and that's about, so this presentation is about the rational approximation of exponential time integration methods. We wouldn't be here if we are not interested in weather simulations, so let me just briefly incentivize this work, where we have always this ongoing demand for an increase in accuracy, and in order to increase the accuracy, one of the main drivers behind that is an increase in the resolution. But if we increase the resolution, that also means that we need to take smaller time step sizes and therefore more time steps. And while 10 years ago, that increase in processor speed, which made this no problem at all over the last 50 years, that stagnated or even declined. And nowadays we face the problem that we still need to complete that full simulation within a specific time frame, namely currently about a 1 hour time frame, and that's getting more and more challenging. And so the underlying question is whether there are time integration methods or whether they need to be developed and how they look like in order to improve this accuracy or in order to reduce the wall clock time, which means that we can again increase our resolution. The test case which I'm using in these slides is based on the single layer atmospheric models. And I think you are familiar with the shallow water equations, otherwise you probably attend the wrong seminar, so let me just skip that part. But let me emphasize two important things, namely, first of all, that the numerics themselves, that they are aligned with the ones in ECMWF's model. For instance, we are using also spherical harmonics, so a global spectral method, and that leads me to the second important thing which I'd like to mention, namely, that all these Helmholtz problems which show up, or Helmholtz-like problems, that all these problems are solved in that global spectral space, which are given by these spherical harmonics, but I'm skipping a lot of details about that, but they play a quite important role in the following slides. The shallow water equations, in the way how we treat them in at least in these, in that slide deck, are treated first in the way of splitting away the fast gravity modes and treating them as the linear parts, and the remaining parts are then treated non-linearly, or alternatively we take the Coriolis effect and the fast gravity modes as the linear parts, and we take the rest of them as the non-linear parts. Well, there could be now different research directions, as I mentioned on the title slide, which we could follow. But instead of just talking about exponential time integration methods, seam Lagrangian methods combined with parallel, the first method, which will be part of the second presentation, and a lot of other things like machine learning and quantum computing, I'd just like to focus on that exponential time integration method in order to make you familiar with how these methods are working, and also to show you some concrete results which you are able to understand, I hope, based on this presentation as well. Okay, so let's talk about exponential time integration method. So let's just say that we have a linear operator given by that scheme. So we have an autonomous linear PDE, which with that L showing L representing the linear operator. Then we can compute a direct solution by given by the solution at ut, by taking the exponential times our t times the linear operator and apply that to the initial condition. And mathematically we can write that as a decomposition into this eigenvector matrix and the inverse of the eigenvector matrix, and this one here would be the exponential of the t times our so capital lambda here is the matrix with the eigenvalues on the diagonal. And let me just emphasize that this is what we could do mathematically, but we would never like to set up that eigenvector matrix directly. So that would never fit into any supercomputer, at least not for the high resolution simulations. There are quite nice properties of that formulation. So the first property is that while we do not have any discretization error in time, so That means we do not have any errors in time. And theoretically, this would also allow us to compute infinitely large time step sizes, or in other words, there is no CFL limitation anymore on that, as we know it from explicit methods. But, well, would be nice if we can just use it, but the exponential itself is really simple to solve for ODE systems, but if you think about PDE systems, it's getting really challenging. And one approach which can be taken is the rational approximation of exponential integrating methods, and that's what I'm explaining in the following slides. Well, let's just take our exponential formulation here, and by using a rational approximation of that one, we can write it as the sum over these betas here, and then these terms here. And it looks, first of all, quite confusing, but just think about these beta coefficients as the weights of finite elements, and that term here is then one of these finite elements, where these alpha points here relate to the placement of these finite elements. And that's how you can read it, and that's how you can approximate that exponential space here. And now the question is, what's the benefit of that formulation? Well, if you just take this initial condition here, and so that's denoted here by these red quads, then we can broadcast that, for instance, to all the racks of our supercomputer. So instead of just taking one rack, we take all the racks, and then we can solve for that system of equations here. That's done independently here on all these racks, and then we can sum up everything over, so that's an element-wise in space summation, and we accumulate all our results at that point here. And now the big benefit of that is that we can parallelize over that sum here. So that's what's depicted here, that we can solve it in parallel and not do a sequential time-stepping method, as it would be the case, for instance, by using Crank-Nicholson. Well, now the question is, what are the best alpha and beta coefficients and how to get to them? And let me just mention that there are different methods available. These are not all the methods, and we have different requirements on them. And sorry to say, but that would be a presentation, a much longer presentation on its own, how that works, how these different methods work, and how they, which properties they have, since that's a high-dimensional optimization space. So let me just stick to the Cauchy contour integration method, the CRX method up here, since once you understand that, I think it's easy to also understand all these other methods which are shown up here. So let's talk about Cauchy contour integral methods. And so given our linear operator, we want to approximate the exponential of our eigenvalues of that linear operator. That means we want to approximate that exponential function, and the exponential function is an analytic function, which means that we can take the Cauchy contour integral method in order to approximate that. And the way how it works is that we take t times our eigenvalues, that's what we want to integrate in the end, and let these dots then denote these t times the eigenvalues, and these are then the eigenvalues for purely hyperbolic problems or purely oscillatory problems, and these guys would be the ones for purely diffusive problems. If we then want to approximate all these exponentials times exponentials of these t times the eigenvalues, we can take the Cauchy contour to enclose them with a contour, and then use a numerical approximation to approximate this exponential function for whatever point in here. That's what's written up here, so that's the contour here itself, and if you take a circle contour, like that one here, and if you take a trapezoidal rule, which just puts some quadrature points here, and applies the trapezoidal quadrature to approximate that contour, we end up with coefficients. So for that scheme here, if you want to approximate that exponential, we end up with coefficients which are given here. That's one important thing, which I will talk about later on, namely this exponential of some r of the radius times some other values here. But in the end, if we then apply some linear algebra, we rewrite our PDE to approximate the exponential of t times the linear operator, again in that rational approximation, where we can directly reuse these beta and alpha coefficients from our exponential function on a scalar. Okay, but let's talk about one particular problem, namely if we have that t times the eigenvalues given like that here. So these would be t times our eigenvalues, these green dots. But now we want to take large time step sizes, of course. So now we need to enlarge these t gets larger. So all these eigenvalues are pushed up here, as shown on this slide here. And in order to approximate these guys here, we also need to enlarge the radius of the circle, which means we need to enlarge it like here. But then we will figure out that this guy here runs into a serious trouble, at least the quadrature here, since these beta coefficients here relate to the exponential of some of the radius. And the larger that one is, the larger these values are getting. And we also know that we have an oscillation along the imaginary axis, and that results in large positive and large negative numbers. In other words, we get cancellation effects, and the way how we can circumvent that is simply to limit it. And by limiting it, we need to rearrange the circle here and also to enlarge the radius here. That's also shown on the next slide, where we end up with a large radius here of the circle. But then we would need a lot of more quadrature poles, but we can again circumvent that by exploiting a similar feature, namely that these quadrature poles are the weights of them, so these beta coefficients, they are close to numerical precision, and we can simply truncate them off. So all these quadrature poles here are truncated off, since we have exponentially fast decreasing values here, and that's then actually how our Cauchy contour integral method, or how the contour of that Cauchy contour integral method looks like. Okay, how do some results look like? Let me emphasize that that's a logarithmic scale here on these imaginary axis. That's the real axis, that's again the complex plane. And that would be, for instance, the stability region of the explicit forward Euler method, where we would have that unit time step size maybe being able to approximate the values accurate also for that point here. And let me just emphasize that we are still extremely accurate of 10 to the minus 10, that's close to numerical precision, by taking 100 times larger time step sizes compared to this state-of-the-art time integration method. But then we need to take about 4,000 poles, but by applying that filter, we can cope with only 300, around about 300 poles for that. But it shows you that we get extremely accurate, and we are not limited in the time step size by taking such a rational approximation. Okay, let's run some studies with that. So the first studies are given by the linear Scheller-Watt equations on the rotating sphere, which is given on that lat long grid here, where we have bumps of different sizes as initial conditions. And after 1.5 days, we stop the simulation, and then we get the bumps at similar to the previous locations, but we also get these meandering curves here, which are caused by the Coriolis effect. If we just take Crane-Nicholson time stepping method and a time step size of 100 seconds, we get these results here, where we get, so the dashed lines are the reference solution, and you see that we get serious defects in here. And if you take even larger time step sizes, defects would be even more increased. Using the Rexy method, and now we are using the T-Rexy method, I'll skip that, but the T-Rexy method is suited for purely oscillatory problems. We can observe that by taking 8 times larger time step sizes, we get less errors in that by still being able to parallelize over that time step computation. And if we take, then the question is, can we do even better than that? And the question is yes, so we can even take a full 1.5 day time step. That means that we run, instead of running just some time steps, we run one huge gigantic time step, and that ends up with this particular form, that we even get our exactly matching contours here without even subcycling the time interval which we want to time integrate. Well, it would be too easy to just say we take the linear equation, since the really interesting effects are generated by the nonlinear equations, and they also lead to a limitation in the time step size. And the results are given here on these slides, where these 3 guys here are the best result for the Rexy methods, where we get either 3 times faster results or 6 times reduced errors for our best alternative method here, which is a strength split Craig-Nicholson method. And I just see that this arrow should point here to that red one here. Sorry for that. But that's exactly what our best reference solution would do if you take a Craig-Nicholson method, and the Rexy method always provides either faster time to solution, which is shown here, or a reduced error, which is shown here. The really interesting effects or really interesting results are then given on the next slides, where we studied the scalability of the Rexy method and whether the Rexy method and the communication might have significant overheads compared to the rest of the simulation. And here we can observe that by increasing the number of ranks, so we have 128 poles for the Cauchy-Contour integral based method here, and if we scale it up to 128, we still see that decrease in wall clock time, and let me emphasize that's again logarithmic scale here, and less means better. And we can observe that the wall clock time for the nonlinearities in the extreme scale, which is that one here, is round about the same as the wall clock time for the linear parts, which we solved with the Rexy, and that's the best Rexy method which we study here. And we can furthermore see that the broadcast time and the reduced time here, that these two guys are not really dominating the overall solution. And that's one of the most important results which we got here, namely that we can say that by using this Rexy as a time-stepping method, that the communication time, at least in this particular case, is not dominating the overall runtime. Otherwise, it might have pointed out that Rexy is not worth to be further studied as part of future work. Okay, let me briefly summarize everything. So for the linear equations, linear equations, there was no limitation on the time step size if you use the T-Rexy method, where we were able to compute even one full time step to run the full simulation over 1.5 days. And if you include nonlinearities, there are more time step restrictions, but we still get an improved error, so reduced error or a reduced wall clock time compared to state-of-the-art methods. As part of future work, we also want to work on Rexy solvers for non-global spectral discretizations, since they are necessary to use, for instance, discontinuous Galerkin methods or spectral element methods with Rexy. And we also work on figuring out a more flexible way to use Cauchy-Contour integral methods on a polynomial contour basis in order to suit your time integration method to what you really need. There's already some work going on with exponential and semi-Lagrangian methods together with Pedro Peixoto, where you already got some results in the plane, and that's what we investigate next on the sphere, with some results which are already quite interesting, but stay tuned for the next time to see that. So thanks for your time, and I'm here for any further questions, of course, then live in the channel itself.